Welcome to Sigma Solver, guys. Before I start the video, I want you guys to smash the like button. This helps the YouTube algorithm and keeps me motivated. And if you are new here, then subscribe to my channel and press the bell icon so that you never miss an update. So without any further ado, let's get started. Today we are going to look at another topic from graph theory, and this is going to be a collection of miscellaneous problems, and we'll deal with them one by one. I didn't do a separate video for each of them because these were inherently small, and so yeah. Alright, so the first question is, answer each case with suitable proof. What is the minimum possible height of binary tree of 2n minus 1 where n greater than equal to 1 vertices? Right. So first we'll see that we are given 2n minus 1 vertices, right? And we know that the minimum possible height of a binary tree occurs when the tree is complete and balanced, correct? So for a binary tree, the maximum number of nodes in a binary tree of height h is 2 raised to power h plus 1 minus 1, right? You can put height 1 and then see what it brings out. So if we do 1, then we'll see that we'll get 3 nodes, right? Which makes sense because height starts from 0 and then goes down to 1, correct? So 0 to 1. Next, so if we are given, let's say 2n minus 1 nodes, then we can say that 2n minus 1 equals 2 raised to power h plus 1 minus 1, which comes out to be 2 times n equals 2 raised to power h plus 1. So on that note, it will be h plus 1 equals log base 2 times 2n. If we do that, this comes out to be the value of height with nodes 2n minus 1, alright. Next, the minimum possible height in this regard would be log base 2 2n minus 1. Obviously, the maximum height would be 2n minus 1 itself, or 2n if we disregard 0th level, because all can be put in the one you can say branch, and then the maximum height can be reached. Alright, then we will come to the next question, which is what is the maximum possible number of vertices in any k level tree. So for that, in a k level tree where the level obviously starts from 0, the maximum number of nodes is when it is a complete tree, right? Just we saw. The maximum number of nodes in a tree of height k, or we can take h as well, is 2 raised to power k plus 1 minus 1, right? So that's the answer to it, and this is something that is quite theoretical, so that's kind of the formula we need to remember. Next, we go to the fourth problem, which is prove that in a simple graph with n vertices and k components can have at most n minus k into n minus k plus 1 by 2 edges. So for this, we'll basically start with the concept that to maximize the edges, each component should be a complete graph. So let n1 to nk be the sizes of the k components such that the entire number of nodes in each of the components sums out to be the total number of nodes, which is n. So the maximum number of edges in the component I can be ni into ni minus 1 by 2, right? Given n is the number of nodes in that particular component size. So we need to maximize the summation of ni times ni minus 1 by 2. So in order to do that, we see that this is maximized when one component has as many vertices as possible, others minimum, that is one vertex each, correct? So then only we can basically increase the number of components. So k minus 1 components have one vertex and one component has n minus k minus 1, which is this many vertices. So in order to maximize the number of edges, we will say that when we will multiply these two for n minus k times, we will get this one. So in this instance, there are n minus k C2 edges in the particular scenario, right? we have n minus k vertices, and for those we will need all the edges. So it's just simple combinatrix. We'll use this one and we'll get this. And obviously this is a conceptual explanation of the proof, right? The actual proof is a bit lengthy, so I have trimmed it off. But if you are interested in exploring the entire handwritten proof for this question, then feel free to join the community by clicking the link in the description given below, and anybody who is the active member of the community will be able to access the given proofs. So I'll provide that link in the description below. Alright, next we'll go to 4b part. Give an example of a plane graph having 5 vertices, 10 edges and 7 regions with complete explanation of your answer. So we are supposed to find a plane graph, right? So for that we have 5 vertices, 10 edges and 7 regions. We'll use the Euler formula to see whether this is even planar or not. So v minus e plus r, where v is the number of vertices, e is the number of edges and r is the number of regions. This needs to be true, correct? This is a theorem, and then we put that, right, and see that okay, r comes out to be 7, so we know that there is a planar graph that would exist. So for that we'll create that, right? You can basically, this will come with practice, and there are some tricks to this particular calculation which are provided in the community notes, right? So those are also there. Then what we can do is basically see the graph here. So it has 5 vertices, right, and there are 7 regions, R1 to R7. The external region is a separate region, and we see all that here, and we can also compare it with the given conditions, right. So this is one type of problem, right, where we are given to find whether a graph is possible or not. Similarly, we can be given like the exact number of edges and stuff. Whether a planar graph is drawable or not, we can also find that, I mean the reverse way. Next, we are now asked to basically draw geometrical dual of a graph, right. The steps to that are: place one vertex inside each face of the original graph. Face means region, okay. For each edge in G that separates two faces, draw an edge between those two corresponding vertices, as in step 1. Dual edge should cross the original edge only once. So the new edge that we are going to draw should pass the original edge only once. And there is one more, which is if there is a dangling edge, right, then we'll have to loop over that region as a different edge in the dual graph. Now since we know what is geometrical dual, let's try to understand, right, what exactly are we trying to build out of this, right. So it is kind of a mirror image, not exactly, but in terms, a mirror image that is built for by drawing new vertices and edges directly over the original layout. Its applications are very much extensive in terms of usage. So map coloring, you can say duals help in converting regions, countries into graph coloring problem, right. As we see in map, they are different colors, but the entire map consists of maybe 3 to 4 colors, right. So that's one problem. Next is electrical circuits and network analysis. So in both these planar electrical networks, dual represent the mesh analysis or dual circuits. You can remember the Kirchhoff laws, the impedance networks, those basically belong to the same chain of thought of duality of a graph. And all the algorithms which we study, like minimum cuts, flows, are simpler or more intuitive ways of using dual graphs, right. So that's the application side of thing. Now we'll take a little example. So we have this particular graph here, right. As we can see that it consists of 7 regions, right. We'll see that there are 8 vertices here, 13 edges, and there are 7 regions, right. And amongst these we need to find the dual for this graph. So for that, first we'll basically convert the regions into vertices. So just looking them side by side, we see R1 has now changed to a vertex, right? And R2, if we see, had this particular edge and this edge with R1, correct? Because this entire external regions is R1. So for those we have like two edges, so two edges will cross. So we see two edges are crossing between R1 dash and R2 dash, correct? Next we go to R2 and R3. Again two edges are there. So here also there are two edges, correct, which we are crossing these two. So you can imagine these edges which are basically depicted in the dual, let me write it here, dual, are basically these, correct, like this. So then we will come to basically R3 and R4, since there is only one edge, so one edge in dual as well. So you can say those edges which separate the regions here convert to basically connecting edges for the vertices. Then for R4 we have R4 to R5, R7 and R6. So we will have those here as well. R4 is connected to all R5, R7 and R6. Then we will see R6 is connected to R1, R5 is also connected to R1. So we will connect those to R1, right, and R7 is connected to R6 and R5. So we will connect these as well, right. Now one thing which we will see is that there is a dangling edge lying all inside R1, right, there is no other region here. So this dangling edge will now convert to a cycle. So as you can see that R1 has a self loop, so that represents this dangling edge. Alright, now this was how you can basically draw a dual for any given graph which is planar. Now we will also discover a very special relationship between the geometrical dual and its original counterpart, which is, if we look closely, we will see that the number of vertices in the original graph becomes number of regions in the dual graph, and the number of regions in the original graph becomes the number of vertices in the dual graph, but the number of edges has stayed the same, right. So this is an important relationship which analysts use very often in solving problems like topological graph analysis and other stuff. Also there are applications in game theory and puzzles. So that's been it. If you want to get any notes or extra documentation for any of these above, then feel free to check out the link in the description and join the community by clicking the link in the description below. If you still have any doubts, then feel free to reach out in the comment section below. If you liked this video, then give it a thumbs up and subscribe to my channel for the upcoming videos. Till then, happy solving.
Hey there, before you go, I've got some fantastic content lined up for you. Over here, we've got some videos and playlists you might enjoy. But first, if you haven't already, make sure to hit that subscribe button and ring the notification bell so that you never miss out on any of our future uploads. Thanks for watching, and I'll catch you in the next video.